This presentation is about the design of thin-wall aluminium beam, which is done in a FE simulation software, Abaqus, and through hand calculations. The beam is designed to be an open section, subjected to 4-point bending as specified in the brief. This type of loading means that the entire beam is subjected to a sagging moment, hence the top flange will always be in compression and susceptible to local buckling. There is no shear force over the central third of the beam. Noting this is important for the improvement made post-FE analysis. In order to reduce the stress in the top flange, it was decided that the section would be asymmetric, as shown, causing the centroid of the section to move up the cross-section, reducing the stress in the top flange and thus the risk of local buckling. Additionally, lips were added so that the flange could be modeled as having simple supports and better resist buckling. Rigidly butt-welded stiffeners were added at regular intervals along the beam length to resist shear buckling in the web, and were designed to resist the buckling load. A range of failure modes were considered to determine the most critical, ensuring this failure occurred within the acceptable range of loads. The critical mode is shear buckling in the web, which caused the beam to fail at 13.5 kilonewtons despite the addition of stiffeners. The next stage involves carefully modeling in Abaqus in accordance to specifications. The loading is applied as uniform traction over load plates, which are small relative to the beam, so they are effectively point loads as assumed. This configuration meant shear punching failure due to concentrated and destabilizing loads can be neglected. When applying the boundary conditions as shown, there was a small discrepancy for the lateral restraints. They did not act over the full height, but just at the lips. This meant initial calculations overestimated the twisting resistance, meaning LTB, or lateral torsional buckling, was more critical. The choice of mesh is governed by computational power, where a 0.8mm quadrilateral mesh of linear shell elements allowed for quick and accurate analysis. The irregularity in the web looks concerning, but results are accurate. By halving the mesh size, only a 1% difference was observed in the lowest eigenvalue in LBA. Numerical inaccuracies were found in maximum deflection for the first two linear bifurcation analysis LBA modes, which are slightly greater than 1. Although this is unexpected in an eigenvalue analysis, given how small the error is, it is not a concern. Our findings coincide with expected numerical behaviors of finite element methods. The most critical failure found from LBA is by global LTB. In this mode, failure occurs with an eigenvalue of 7.71 and a corresponding total load of 15.42 kilonewtons. As the beam was designed with a failure load of 13.5 kilonewtons, the actual load exceeds the design load by a factor of 1.14. The failure load also exceeds the maximum load specified in the brief. This suggests that assumptions and simplifications in hand calculations were conservative, leading to a safer but inefficient design. Moreover, the expected failure mode was shear buckling in the web, which differs from the FE analysis. The disparity shows that the initial overestimation of the LTB resistance and underestimation of the shear resistance was evident. There are many reasons that contribute to this difference. The first is how lateral restraints are defined. The beam was designed with the entire cross-section at both ends and third points fully restrained laterally. However, in the FE model, only the sections shown in red are restrained. This resulted in an underestimation of effective length for the calculation of the critical moment, which further magnified by the lateral restraints on the opposite flanges. For a more accurate representation of LTB, the new effective length should be corrected by considering the length of the diagonal. The next cause of difference is the definition of boundary conditions. This should be reconsidered such that at one end is simply supported with fixed translation, while at the other is free in rotation and translation. This results in a 52% utilization of LTB resistance. The last reason for the difference is the calculation of cross-sectional properties. Stiffeners and end plates were not considered in the hand calculations of the second moment of areas IYY and IZZ. This would have underestimated the beam's actual bending and compression buckling resistance. Following the linear eigenvalue buckling analysis, geometrically and materially nonlinear analysis with imperfections included, GMNIA, is used in the next stage to verify the strength capacity that accounts for real-world conditions where imperfections may occur during manufacturing and assembly stages. Incorporating such nonlinear material properties allow for accurate calculations of stress distribution, while nonlinear geometry takes into account the reduction of capacity from stiffness reducing effects due to residual stresses and inelasticity. By testing different scenarios with a bias involving the modes with the lowest eigenvalues, the most critical combination can be determined. As higher buckling modes have little chance of occurring, tests conducted mainly contain the most critical LBA mode number 1. It was found in the most critical case was a combination of modes 1 and 2 with excess deformations at the ends with high stress concentrations on top flange, 1 being LTB, 2 being distortional buckling. This combination of modes were chosen because of the similarity in deformations. These failure modes 1 and 2 dominate, and adding additional failure modes such as 3 and 4 does not decrease the load capacity. This combination leads to a failure load of 12.8 kN, which is still greater than the minimum required load. It is lower than the design failure load, which is to be expected, given that initial calculations did not consider interaction between modes. Another set of cases involving introduced imperfections in modes 1, 3, and 6, noting node 1 is LTB, mode 3 is a combination of distortional and web shear buckling, and mode 6 is compressive buckling in the web. These failure modes are common in I-beams, and a combination of these modes could provide insight on how different failure modes interact. Tests were performed by introducing imperfections to mode 1, 1 and 6, and 1, 3, and 6 separately. While the beam was sensitive to global imperfections introduced in mode 1, it is insensitive to other local imperfections. This conclusion coincides to the LBA, where it identifies mode 1 as being the most critical. Looking back at the 2 load cases mentioned, it is evident that interactions of different failure modes cause the load capacity of the beam to decrease, and that a target load of 13.5 kN was not reached for the most critical case. This conclusion shows the importance of including imperfections in design applications. It should be noted that even in the most critical case, there is no complete structural collapse after failure. A fairly stable failure mode was observed, as shown in the load displacement graph. This is because the governing failure load is LTB, which in comparison to other failure responses is fairly stable. While the beam failed before the target load of 13.5 kN, it failed after the minimum required of 12 kN, thus leaving some space for improvement. The first aspect of improvement is the stiffeners. These had been designed conservatively by assuming a maximum internal shear force along the length of the beam. Simple structural analysis shows that the internal shear force was 0 in the middle third. This means that having as many stiffeners in the middle as in the rest of the beam is theoretically unnecessary. Indeed, the LBA shows that the shear buckling of this region did not occur until the 6th mode. The second aspect to be redesigned was the end plate resizing. The original end plates were unnecessarily wide due to the misinterpretation of typical design characteristics and covered the entire width of the top flange. Testing the shortened end plates in Abaqus with no other changes reduced the first eigenvalue by only 0.01, demonstrating unnecessarily large they were. The improved design firstly replaces central 2 stiffeners with a single one. Attempting to discard these stiffeners without replacement caused the beam to fail before 12 kN, meaning the new central stiffeners was required. This is likely related to the local contribution made by the stiffeners to IZZ, which influences resistance to the critical failure mode, LTB. The end plate was also reduced to cover only the width of the bottom flange. The saving due to the reduced material and labor costs are not particularly large. However, if this design were to be used multiple times in many parts of the structure, the saving could become much more significant, as well as having an effect reducing carbon emissions. The new design failure at a load of 12.24 kN, where the deformed shape and the load displacement curve are really similar to that of the original design. This is unsurprising given the changes were relatively minor. In conclusion, the design can be summarized by a set of seemingly contradictory statements. Initial hand calculations resulted in a beam design that was expected to fail due to web buckling at 13.5 kN. However, lateral torsional buckling, a mode that was under-designed for due to incorrect assumptions about lateral restraints, in fact turned out to be the most critical during LBA. Yet despite this unexpected failure mode, the beam turned out to be too safe with a failure load above the brief's limit. Fortunately, when imperfections were added to the beam, the critical combinations of imperfections gave a critical failure just above the minimum required. The end result was a beam that is fairly optimized with some contingency for safety. This meant that only very small, minor improvements to the beam were possible, such as removing a couple of web stiffeners and reducing the size of end plates. Thank you for listening to the presentation.